The next metal we're going to talk about in the abundant metals, remember we just finished talking about iron, is aluminum. We use aluminum all the time. Drink our beer out of it, we drink our soda out of it, we fly around in it, right? Airplanes are made out of aluminum, our bass boat's made out of aluminum. We use it for all kinds of crazy stuff, particularly because it's very lightweight and it's fairly strong. We don't think about it as strong in the case of a can because it's very thin, but when you have a lump of aluminum, it's very, very rigid, right? So one of the places where we use it the most that you might not think about is the aerospace world, right? Making airplanes. The geologic formation of aluminum is pretty interesting. Aluminum comes from an ore called bauxite. And bauxite is an interesting mineral that doesn't form from magma or anything like that. It actually forms within the soil or within decomposed rock. So the easiest way, and I've got a figure I'll show you, but if we think about kind of how this works, let's say we've got some bedrock here, and that bedrock is something like a granite. I'm just going to do a case study with one mineral. So the reality is actually even more complicated than this. So if we think about a granite, most of a granite is this funky mineral called a feldspar, and a feldspar is a big group of minerals. You can actually see here, this is one of my favorite ternary diagrams of the feldspars. You can see the alkali feldspars and the plagioclase feldspars, potassium, sodium, and calcium. But if you look closely at this diagram, you can actually see a few places where they have the chemical formulas labeled. And in every case, there's aluminum in there. So feldspar is actually what we call an aluminosilicate mineral. That means nothing to you, but the alumino part should mean that mineral has aluminum in it as a component. Muscovite, which you might know of as mica, that also has aluminum in it. There are amphiboles have aluminum in it. All kinds of stuff in a granite has aluminum in it, but they're present in the minerals at very small percentages. So now, if we think about this granite decomposing, water is going on, and places that get really extreme chemical weathering. The factors that affect chemical weathering are moisture and heat, right? So really hot, really wet places, the rocks decompose much more quickly. The rainforest, that's probably the best place you could imagine. Right? In a rainforest, we have maximum chemical weathering that's occurring. And so as that happens, this water comes through, and these minerals begin to dissolve, they begin to do all sorts of other things. They begin to do all kinds of weird stuff. So here, I actually drew, this is the chemical formula of one type of feldspar, potassium feldspar. So here we've got some potassium, some aluminum, some silicon, and some oxygen. So when this mineral undergoes chemical weathering, it dissolves, and the potassium ends up in groundwater. It's soluble, it goes away. The silicon ends up in groundwater. It's soluble, it goes away. The oxygen ends up in groundwater, it goes away. All of this stuff is leached out of the system by groundwater flowing through. Aluminum is not soluble. It gets left behind. It's the one friend who got left behind at the party, if that makes sense. And when that happens to an extreme amount, there starts to be lots of aluminum left behind, and that's when we get the formation of bauxite. So bauxite, which is aluminum ore, really requires, the right type of geological ingredients, but also extreme chemical weathering, right? Just flushing with salt, with warm water that's dissolving all of these things, leaving just the aluminum behind. Not that uncommon, but really in tropical places or places that have, areas of their country that they do see that type of chemical weathering. Bauxite as an ore itself is really strange looking. It's kind of these weird pea-sized masses. You can see here is an image of bauxite. And then to mine it, well, if we think about what our resource is, we have soil here now. So this is not a ore that we need to go really digging deep for. This is an ore that basically occurs at the surface. And so the way that we mine it is essentially a strip mine. You can see here again in this diagram exactly that type of strip mining of fairly low tech, because also if we think about places where bauxite ore is going to occur, they're going to be tropical, and not in all cases is there going to be a very large financial system there to develop really big mines. Oftentimes these places are fairly poor. So you get some machinery, you go in and you scrape out the bauxite. But really the story of aluminum changes there. So one thing that we're going to examine is getting from bauxite ore to finished aluminum, the kind you would use to make a beer can. That step is pretty significant. It takes a lot of energy to do that. When we think about where bauxite occurs, those tend to be, countries that are less developed, and they don't generally have very cheap power or very reliable power. So the reality with bauxite is we usually mine it somewhere, put it on a barge, and take it somewhere else on planet Earth that has really cheap power. Actually, the Pacific Northwest is a place where that happens. We bring bauxite from all over the world here, and we use hydropower because it's fairly cheap, because it's very, very, very energy intensive. We'll look at one diagram on how we smelt aluminum, and one of the takeaways that I hope that you'll get from that is how much energy is used in the production of aluminum. This is a terrible drawing of North America. But West Coast, Baja California, Florida, South America, I don't know. I did it really quickly. I didn't look at a map just from memory. So thinking about bauxite and getting from the ore to aluminum, one of the places where we actually mine a lot of this stuff is down here in Brazil. So Brazil, tropical rainforest. You can see this is actually an example of a Brazilian bauxite mine. Everything's oxidized, fairly red, and you can see the machinery is in there pulling that ore out. What we would generally do at that point is put that ore on a boat. There's our little sailboat. We would travel through the Panama Canal, of course, and up here into the Pacific Northwest. And we would, at that location, take advantage of the cheap power and get ourselves some beer cans, basically. But again, the way that this works is not as simple as getting enough energy to break the oxidation bond, which we saw with iron, and we actually see that with a lot of other metals. Bauxite ore is a little bit more complicated. And so I don't want to go so into the kind of electricity of the whole thing, but you can see here in this diagram, essentially what we do is we dissolve the aluminum in a fluid so that it's soluble in these certain acids, right? They'll dissolve the aluminum out of our bauxite. And then we still need to break some of those molecular bonds, and to do that, we zap it with electricity continuously. And so you can see in this diagram, we've got these big kind of graphite anodes, which are the positive lead. It is wired up a light switch, probably knows how this works. And then we have the steel casing and a graphite cathode, which is depleted of electrons. And the flow of electricity flows through that fluid. And the electricity creates enough heat that in that fluid, as the electricity is moving through there, aluminum starts to separate, and we get molten aluminum that settles to the bottom of that kind of electrical pond, and then that can be pulled off the bottom in a similar way to a blast furnace. So, massive amounts of electricity. Again, not something that's really economically feasible to do in Brazil at the large scale. It makes much more sense to bring it somewhere where there's cheap power. They do it down south as well, right? We've got just an abundance of coal power. So getting the aluminum from ore all the way to usable aluminum is significant. And we're going to take a little journey through here. I'm going to write up a bunch of numbers and stuff, and we'll kind of talk about what that really looks like, right? We'll talk about how we get from the cost of aluminum ore to finished product aluminum. And we'll see the stages along the way. It's actually pretty interesting. So the numbers will be not super important, but they'll help you follow the story. The biggest thing with aluminum, as I've said over and over, is the amount of energy that it takes to get it from its ore. So actually, I put up some numbers in, and there is definitely a range kind of depending on the exact setup. So to produce 1 pound of finished aluminum, which, you know, famously aluminum is pretty light, but from bauxite, so from ore, we're in the range of, in the kind of the high twos, so 230 to 310 megajoules. That's a significant amount of power. That's equivalent to, you know, 65,000 to 90,000 kilowatt hours. Right? Imagine what your power bill would look like if your usage was that high, right? Oh my gosh, it's really expensive to do that, right? Because power is not free. You have to do this somewhere, and you're paying a power utility to produce your pound of aluminum. But this is where we start to see aluminum famously, once it's separated into just the aluminum molecules, it's happy, right? At that point, it's fairly inert. It doesn't want to react. And so producing aluminum from aluminum is actually really straightforward and pretty simple. So if we were to process aluminum from pre-existing aluminum, we're talking about recycling here, right? You pile up your beer cans, your soda cans, or your spare aluminum that you may have laying around. In that case, to produce 1 pound of finished aluminum, it takes 11 to 17 megajoules, significantly less, with a cost that's significantly less. So it's much, 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 much cheaper to produce aluminum from aluminum. And actually, as a result, because again, cash rules everything around us, the Wu-Tang Clan taught us that, right? Most of the aluminum that's been processed, especially for large applications like aerospace applications, most of the aluminum that's gone through this processing has been reprocessed multiple times. And it's not a resource that, you know, eventually kind of peters out like paper, right? You can only recycle paper so much before the fibers become too short and it's unusable. Aluminum is infinite, right? We're just rearranging the atoms over and over and over and over again. So the portion of aluminum that has been processed that no longer exists is the stuff that's sitting in the dump, right? So when you throw your beer cans away or you throw your soda cans away, that then goes and sits in the dump, and that's not able to kind of be reused. So I'd mentioned Brazil, right, as a place where this process all happens, right? This notion that we take it from a rainforest to somewhere where there's cheap power because it's so expensive to do. I just wanted to give you a quick rundown. You can see this list here. This is where aluminum is produced. Keep in mind, think back to one of those first few videos. Bigger countries are going to be more significant, right? And countries, obviously in this case, that need to be tropical, right? You need to have a situation where that chemical weathering is extreme enough that it's going to be creating bauxite ores. And so we can see, topping the list is Australia. Going down from there, China, Brazil, India, all fairly large countries. We get into Guinea, Jamaica, Russia, Kazakhstan, Suriname, Venezuela, Greece, Guyana, Sierra Leone, Vietnam, United States, which is pretty tiny, and then kind of other after that. So we do a little bit, but really the fairly tropical places, and you not only have to be tropical, you have to have the right geology that will decompose and has enough of those aluminosilicate minerals. And then I wanted to kind of get back to this notion of the amount of energy used. So you can see this is a pretty colorful diagram, actually, blue, red, and yellow, showing the amount of energy to produce ore, or to produce that metal from ore, to produce that metal essentially from itself, or to do a hybrid. So you can see the steel on the left, aluminum in the middle, copper on the right. Aluminum has this massive, massive, massive blue spike, higher than any of the other things, right? And so it's so expensive to make aluminum from bauxite that in many cases it's cost prohibitive, right? And so you can see to create it from recycled is much, much, much lower. So when we think about recycling, copper should come to mind, right? There's a lot of money in recycling copper. But the thing that we do recycle the most, or think about the most, is our aluminum cans, because it's so easy to recycle them, and it's so much more efficient for the system as a whole. Actually, this is a diagram that looks at some of these recycling rates, kind of how they've changed over the years. You can see we go back to 1955. I know, especially when you think about recycling aluminum, we always kind of go to the beer can model. But remember airplanes, right? Airplanes are one of the largest sources. And so even in the 1950s, we were recycling a lot of aluminum, although maybe the general public wasn't recycling aluminum from their homes, right? We were recycling on an industrial scale. But then if we look at how that rate changes, over time, we're at about 50%, right? So about 50% of our use of aluminum gets recycled, and then that number is getting better and better all the time. And frankly, companies who produce aluminum goods, whether it be for the aerospace or whether it's for the canning world, the packaging world, they want cheaper goods, and if they encourage you to recycle, then there's a larger pool of cheaper aluminum for them to buy, right? So in a weird way, they want us to recycle it as well, right? Because their cost for raw materials is much lower if it's from a recycled source. Okay, so that's going to finish up abundant metals. We're going to move on to the next module in the case of scarce metals, which include ferroalloys, then also some rare metals and things like that. So we'll get a chance to get into some more shiny and financially productive metals in the next module. Okay, we'll see you then.